Okay, in the previous video, we looked at substitution reactions of alcohols, and a lot of that was review, but we learned a couple new reactions. In this video, we're going to look at elimination reactions of alcohols, and I think this is pretty much all review from Orgo 1. Okay, so last semester we saw that alcohols could undergo elimination under acidic conditions. And so, in particular, if we use concentrated sulfuric acid, we could convert the alcohol into an alkene. If we have a tertiary alcohol, it's going to proceed via an E1 mechanism. So we'll start with a proton transfer, converting the alcohol into water, which is a good leaving group. That water will pop off in the loss of a leaving group, giving us a carbocation, and then we'll finish with a proton transfer that will give us the alkene. Now, one disadvantage of an E1 mechanism in synthesis is that we can't control which products we get. And the E1 is always going to favor the more substituted alkene. So in this case, this is going to be our major product, and we have no way of forcing this to be the major product. Right? Another disadvantage of synthesis using E1 mechanisms is that carbocation rearrangements are also possible. Now, under acidic conditions, we've previously looked at what happens with a tertiary substrate. We also see elimination with secondary and primary alcohols. For primary alcohols, they most likely follow an E2 mechanism. However, we can't control the regiochemistry like we can if we did the elimination using a strong base, right? If you remember, if we choose a bulky base, we can get the less substituted product, the Hoffman product, or we could use a non-bulky base and get the Zaitsev or the more substituted product. In this case, we'll always get the more substituted alkene. So to my mind, I think the better way when we're doing synthesis, even though I've used a lot of this video talking about elimination under acidic conditions, I think the better way to do that is, or the better way to get elimination is to convert the alcohol into a better leaving group. And so the easiest way to do that is to react it with TSCl and pyridine, right? That converts it into a tosylate. And now the advantage of this is now I can do elimination with a strong base, and I can control which product I get by choosing a bulky base, which will give me the less substituted alkene, or I can use a non-bulky base, which will give me the more substituted alkene. So in general, I think we prefer E2 reactions over E1 reactions. The E2 pathway is not susceptible to rearrangements, and we can control the regioselectivity. And even doing reactions under acidic conditions with primary and secondary substrates, I still can't control the regioselectivity. So I think very often in synthesis, our best bet is to use convert the OH into a better leaving group, and then use a strong base to get the elimination. All right, so let's again finish off with a couple examples. And so I want to indicate which will be the major product. So I probably should have put here not only using H2SO4, but it's going to be concentrated H2SO4, right? Dilute H2SO4 is actually going to prefer the addition products rather than the elimination products. So in this case, we'd want to use concentrated H2SO4. Now I have a tertiary substrate, so this is going to proceed via a E1 mechanism. Now I can't form a double bond here because I've got no hydrogens to eliminate. So my possible products are going to be forming the double bond here or forming the double bond here. And so I can get this product or that product. And then we're also asked to indicate which is the major product. Because this is going to proceed via an E1 mechanism, the more substituted alkene is going to be the favored product. All right, so one final example. In this case, we're first reacting this with the TSCl in pyridine, which is going to convert my alcohol into a good leaving group. Then I'm using a bulky base, so I'm going to get elimination. We're going to follow an E2 mechanism. Now again, I can't form a double bond here because I've got no hydrogens to eliminate, so my options are to form a double bond here and here. So if I do this one first, I'm going to get this product. And it's always good to consider, is the product I'm forming stereoisomeric? In this case, this first one is not, so I don't have to worry about cis and trans isomers. But when I form the other product, this is stereoisomeric. And so in this case, I formed the two highest priority groups are on opposite sides. So this is the E isomer. I can also form the Z isomer. So I'll get 3 products in this case. Okay, but when it wants us to predict the major product, because I'm using a bulky base, it's going to prefer the less substituted alkene, and so this will be my major product.